Hi, and welcome to this video on floats. We're going to start by looking at the internal representation of floats. How are real numbers, floats, actually represented in the computer? So the float class is what Python uses by default for real numbers. So when you type, a equals 10.5, then the default class that is used by Python is called a float. Now there are other ways to represent these real numbers, and we'll look at that shortly in the decimal class. But the float is the more common one to use because decimal has some disadvantages, such as speed, takes up more memory, they're a little bit more complicated to use. Now the Python float, and I'm talking about CPython in particular, is actually implemented using the C double type, the double precision floating point type in C, which is usually implementing an IEEE standard for floats, and it's this standard here, the IEEE 754 double precision binary float. That's a mouthful. Very often it's shortened to just binary 64. But it is a standard way of representing floating point numbers in computers, and many languages will use it, not just Python. C uses that, as well as many others. Now, the float uses a fixed number of bytes. Remember when we looked at integers, we saw that integers could grow as large as we wanted to, and it would just take up more and more memory space as needed. Floats are not the same. Floats are a fixed width. In other words, they have a fixed number of bytes that can be used to store and represent floating point numbers. In particular, it uses 8 bytes, and that means 64 bits. But Python also has some overhead too with objects, which means that in reality, when we create a float in Python, we're actually using up 24 bytes. But no matter how large our number is, as long as it fits within what a float can actually contain, we only are using 24 bytes. Now, this 8 bytes and 64 bits kind of depends on the C compiler as well. So in this case, what I'm really referring to is my version of Python, which is CPython 3.6 on a 64-bit operating system. Depending on how it was compiled, how the Python interpreter was compiled, the C double may actually be a little different. So that kind of depends. But in general, more often than not, you're using the standard CPython interpreter, which means you're dealing with a 64-bit float. Now, those 64 bits are assigned to different parts of a real number. And let's take a look at that. So the first thing is we need a sign, right? Is it positive or negative? So we'll use 1 bit for that. And in general, we'll use 0 to indicate that the number is positive, and 1 to indicate that the number is negative. Now, we also have an exponent. And what do I mean by an exponent? Well, if we look at this number, 1.5 e to the negative 5, right? This is the same thing as writing 1.5 times 10 to the negative 5. And this notation is standard in Python. You can use that to create, a literal for a floating point number. The case of e can also be lowercase, it doesn't matter. But this number here, this negative 5, that is the exponent. So any number can be written as a number times 10 to the power of something. And that something is the exponent. And that exponent, 11 bits are reserved for it, which means that the exponent's range can be from a minus 1022 to 1023. And then the rest of the 64 bits, which is 52 bits, is taken up by the significant digits. So that gives us about 15 through 17 significant digits, and I'm talking about base 10 digits, so 0 through 9. Now, what are significant digits exactly? Well, you can think of it very simplistically as all the digits except leading and trailing zeros. It really has to do with how the numbers are represented in memory and the number of digits that we need to represent that number in memory. But simplistically, just remove leading and trailing zeros, and that's the number of significant digits you have in the number. So for example, 1.2345 has 5 significant digits, right? Because you need all of these digits to represent the number. Same thing, 1234.5 also has 5 significant digits. Now it's not the same number, right? And even though it has the same digits, it's not the same number, but it has the same number of significant digits. Same thing with this number here, 1, 2, 3, 4, 5, with 1, 2, 3, 4, 5, 6 zeros after that. Well, that is also a number with 5 significant digits, because this is really nothing more than 1, 2, 3, 4, 5 times 10 to the 6. And so the 6 is the exponent. Well, that's stored in the exponents. And the 1, 2, 3, 4, 5 are the significant digits. So we still have 5 significant digits. Same thing here. We have 5 significant digits, right? These leading zeros don't matter. They're going to go into the exponent. 1, 2, 3, 4, 5 times 10 to the negative 50. Again, we have 5 significant digits. This is the exponent, negative 50, but we have 5 significant digits. Same thing here, 1.2345 E10, right? That is also 5 significant digits. So the first thing we're going to look at is how can we represent real numbers using a decimal or a base 10 version. So we can represent numbers as base 10 integers and fractions. And we've seen how to do base 10 integers. Those are the regular integers we use every day when we speak. 10, 120, 135. These are base 10 integers. They're in base 10. But what about what comes after the decimal point? Well, we can express those as fractions, and in base 10 we can express them as decimal fractions or base 10 fractions. So what do we mean by that? Well, let's take a look at an example. Let's look at 0.75. This is 7 divided by 10 plus 5 divided by 100, right? This is the tenths position, this is the hundreds position. So we can rewrite this as 7 times 10 to the negative 1 plus 5 times 10 to the negative 2. Notice how we have a digit times some power of 10. Now these digits are always going to be between 0 and 9. And in this case, this expansion only required 2 fractions with non-zero numerators, which means that we have 2 significant digits. And we can see it from the number here as well, that we have 2 significant digits. What about 0.256? Well, very similarly, this is 2 over 10 plus 5 over 100 plus 6 over 1,000, which we can rewrite in this notation here in this form. So we have these digits between 0 and 9 and powers of 10. And you'll notice that as we move from left to right, the powers of 10 become increasingly negative. And in this case, well, we needed 3 of these fractions to actually define the number, and this means that we have 3 significant digits. And again, we can see that from the numbers. Now, of course, we can also have numbers before the decimal point that are other than 0. For example, 123.456. Well, as we saw before, this is 1 times 100 plus 2 times 10 plus 3 times 1 plus 4 over 10, 5 over 100, 6 over 1,000. So now we've just done that expansion basically to the left and to the right of the decimal point. In this case, we needed 1, 2, 3, 4, 5, 6 of these terms to define the number, and we therefore have 6 significant digits. Now we can rewrite this as 1 times 10 to the 2 plus 2 times 10 to the 1 plus 3 times 10 to the 0, and then after the decimal point, 4 times 10 to the negative 1 plus 5 times 10 to the negative 2, and so on. And you'll notice that we just have decreasing powers of 10. So as we move from left to right after the decimal point, we have increasingly negative powers of 10. As we move from right to left before the decimal point, we have increasing powers of 10. And in this case, as I said, we have 6 significant digits. So in general, right, if we try and generalize this formula here, this is what we get. We get that our number, right, this number here, is equal to some sum of a digit, which is going to be between 0 and 9, times some power of 10. Right? This is just generalizing this formula here. Now we're still missing the sign. So we're going to bring in the sign and we're going to say, okay, sign is going to be some variable, let's say, that's equal to 0 when the number is positive and negative 1 when the number is negative. So now we can rewrite this formula here to also include the sign of the number as follows. If we take negative 1 and let's say it's a positive number, then negative 1 to the power of 0, well, that will be equal to 1. Any number to the power of 0 is 1. Well, except for 0 to the power of 0, which is more of a convention, and that can depend on how you want to look at it. But if the number is negative, then we have 1 for the sign, right? The sign is 1 if we have a negative number. So we have negative 1 to the power of 1, which is negative 1. So we'll end up with a negative sign on this expansion here, which is what we're looking for because we want a negative number. Now, one thing that comes up when we do expansions like this is that some numbers cannot be represented using a finite number of terms, right? And again, this is the expansion here. Well, obviously, numbers such as pi or square root of 2 don't have a finite representation, right? We cannot write, we don't stop here after the decimal point. We have an infinite number of digits after the decimal point, and same thing for square root of 2. So obviously, this summation here is going to be infinite. We're going to end up with an infinite series. So that's pretty obvious. But we also have rational numbers. Some rational numbers cannot be represented using a finite representation, a finite sum. Like 1/3. We write 1/3 as 0.333. We put that little dot up here to indicate that that 3 is recurring infinitely. So 1/3 is 0.3333. And it doesn't matter how long you keep saying 3, at some point, if you stop saying 3, you are no longer exactly equal to 1/3, you just have an approximation, which might be very close, but it's still an approximation because, at some point, we have to stop counting those numbers out. And the same thing with a computer. A computer can't store an infinite number of digits or an infinite number of numbers after the decimal point, and therefore, we cannot represent 1/3 exactly using this kind of notation or this summation here. So again, this is just 3/10 plus 300 plus 3,000, right? This is just this expansion here. And so that's an infinite sum. Okay, so we saw how to represent in decimal. We saw that we had sometimes finite sums like 0.75, but we also have infinite sums sometimes when we have 1/3, the rational number 1/3. So now let's take a look at how we can represent these floating point numbers, not in base 10, but in base 2, since that's what we have to work with when we're dealing with computers. We only have bits, zeros and ones. So instead of powers of 10, we're going to use powers of 2. And our digits are going to be just 0 and 1. Whereas before, our digits were 0 through 9. Here it's just going to be 0 and 1. So let's take a look at a binary float. So this is a binary number, 0.11 base 2. So we do have this decimal point. I don't know if you'd call it a decimal point or maybe a binary point at this stage. But anyways, so what is that equal to? Well, if we're talking about powers of 2 instead of powers of 10, then we have 1/2 plus 1/4. Now this is the base 10 equivalent, which is 0.5 plus 0.25, which is 0.75 in base 10. So 0.11 base 2 is 0.75 base 10. So let's look again at this expression here, and let's rewrite it in the same way we rewrote powers of 10. So we have 1 times 2 to the negative 1 plus 1 times 2 to the negative 2. Now similarly, we can look at this number here, 0.1101 base 2. Well, that's 1/2 plus 1/4 plus 0/8 plus 1/16. Again, these are powers of 2. So if we calculate the number, we get that that's equal to 0.8125. So 0.8125 base 10 is 0.1101 base 2. And again, we can rewrite this expansion as follows. It's 1 times 2 to the negative 1 plus 1 times 2 to the negative 2 plus 0 times 2 to the negative 3 plus 1 times 2 to the negative 4. You'll notice all our digits are either zeros or ones, and these denominators here are powers of 2. And again, they become increasingly negative as we move from left to right after the decimal point. So this representation is very similar to the one we had with decimal numbers, except we're just representing a number using base 2. So a binary representation is then given by this formula here, which is exactly the same as what we had previously, except that these digits now will always be 0 or 1, And instead of powers of 10, we have powers of 2. But same thing. Now, as you can imagine, we also have problems representing certain numbers in a finite number of terms, right? Just like we had a problem using 1/3 in our decimal expansion, we also have problems representing certain numbers in a binary expansion. And a very simple example is 0.1 or 1/10. Now that has an exact representation in decimal. It's 1/10, right? It's 0.1. But not so in binary. In binary, we do not have a finite representation. This is the binary number that we have to use to approximate 1/10 or 0.1. It is 0.0 and then this sequence of bits 0011 0011 that just keeps recurring. So this is just like the example we had with 1/3, except that with 0.1 we have a similar problem. We cannot represent that exactly in base 2. So let's take a look at what this means. So if we just expand this out to fractions, right? So we have 0, this first position is 2's, or 1/2, this second position is 1/4, so third 1/8, 1/16, 1/32, just powers of 2. So we can write it out this way, right? We have 0/2, 0/4, 0/8, 1/16, 1/32, etc. And let's start actually calculating what those numbers are. They should add up to 0.1. Now they'll never exactly add up to 0.1 because this sequence of numbers is infinite. This is an infinite series. All right, so tossing out all the 0 terms in these fractions, we end up with these. And the first fraction is 0.0625. So if we were to stop at the first significant digit here, 1, right, we would end up with actually 0.0625 in decimal, which is not exactly close to 0.1. But if we keep going to more and more of these bits, let's add in 1/32. So now we have 0.09375, much closer to 0.1, plus the remaining terms. And we can keep adding, now we can add the 1/256 into this, so now we get 0.09765,625, okay, etc., etc. Now, you got to be careful, right? It looks like, oh, we're undershooting the 0.1. Well, we may be at this point, but sometimes you could be overshooting as well. So, your approximation to the number that you're trying to represent may be slightly larger or slightly smaller than the exact value. And we'll see examples of that when we look at the code. Okay, so that's the binary representation of a number, of a decimal number. And that is indeed how it's stored in the computer. So, as we've seen, some numbers that do have a finite decimal representation, like 0.1, right, do not have a finite binary representation. Now, of course, some do, right? Not every number is going to have an infinite binary representation. In fact, we saw some. 0.125, right, was 1/8. That's a power of 2 in the denominator, so we know that we're going to get an exact binary representation. Right, so 0.75 base 10 was 0.11 base 2. Again, that's a finite representation. Same thing with 0.8125 in base 10. That has this binary representation, 0.1101. That's also finite. Now, because these are finite representations, this means that we have an exact float representation. So when we type in 0.75 in Python, exactly 0.75 will be stored. Okay, it will be precise. On the other hand, if we say a equals 0.1, we are not going to be storing 0.1 exactly. It's going to be that 0.999, and a bunch of numbers after that, right? Because it is this infinite representation. So because of that, we only have an approximate float representation in Python. And this isn't a shortcoming of Python. This is going to be true of any computing language. It's because of the fact that computers use binary, use bits, zeros and ones, and so therefore at some point we have to basically transform our decimal number into a binary number. And because of that, we run into these approximation issues. So let's switch to some code and see how all that works, and we'll do that in the next video. Thanks for watching, and I'll see you in a bit.